All right, so let's talk about horizontal and oblique asymptotes. So that's basically asking ourselves what happens when x is very, very large. This is the sort of the classification of the end behavior for rational functions. Oblique asymptotes, sometimes I see them referred to as slant asymptotes. Oblique is a word that is not super commonly used in like casual everyday speech. It's a little bit of a fancy word, but you might have heard them called slant asymptotes, and that's just a diagonal line. Sometimes, as x gets very large, your function doesn't approach one particular y value, and it might gradually approach a diagonal line. So we'll look at that case. Sometimes your rational function might approach a horizontal line, or sometimes the function it just gets really, really big. So just like polynomials, they want to go to plus or minus infinity when x is super duper large. That's it's also a possibility, and it depends basically only what happens for large x. It only depends on the degree of the numerator and the degree of the denominator. So the summary is basically here. So if the denominator wins out, so if you have like x plus 1 over x cubed plus 7x minus 3, well, imagine you plugged in x equals 1,000. Well, this would be in the billions, and this would just be only 1,000, and the denominator is getting super duper huge. The y values get super duper small, and so you can think that the denominator wins, or the denominator grows much more rapidly than the numerator. And because here are the highest order terms, x to the third in the denominator is growing faster than x to the first in the numerator. And that's this right here. If the numerator and the denominator have the same degree, so what if instead I had x cubed plus 3x minus 1? Well, now let me just throw in a 2 here, and maybe the coefficient of maybe put a 5 down here. So the sort of second bullet point is, okay, now the numerator and the denominator polynomials have the same degree. Well, the numerator basically looks like twice something. The denominator looks basically like 5 times that same something. And then a lot of smaller, lower order terms that don't really matter very much in the long term. So same degree. And the numerator, maybe the numerator is 2 billion, and then the denominator is like 5 billion plus, So they're two things of the same order of magnitude, but then this one has a coefficient of 2, that one has a coefficient of 5. The rest of it kind of doesn't really matter. You can experiment with this numerically. I'll also show you an algebra trick in a minute here to sort of see the same result. But I claim that this is what always happens. If the degrees are the same, then you just divide the two coefficients of the highest order terms. And that'll do it. That's the in behavior. So that works for as x goes to positive values and as x approaches minus infinity. So plus infinity, if x is a big positive number or a big negative number, this kind of function is going to have y values that are very close to this. Case number 3 is if the numerator has degree that's exactly 1 larger than the degree of the denominator, then you have to do long division, and then the what you'll have to be left with is a linear function plus something that goes to 0. And then so the whatever ax plus b will describe the slant asymptote. So that'll be the last thing that we do. So let's sort of look at these other ones first. So let's talk about So I just want to illustrate the general case by looking at one specific case. So I just want to illustrate why this is true just once, but then this is just a fact that you can always appeal to in the way we're teaching it. So in some classes they might make you reproduce this fact or this logic, but I'm going to show you the reasoning once, and then from then on it's a standard fact that you can just use. So yeah, the degrees are the same. So the coefficients are 3 divided by 5, and that's the end of the story. But just let's explain why. So what I'm doing here is I want to factor out x to the 5th divided by x to the 5th from this. So anything that's of a smaller degree, I need to give it a little bit more. And then we'll see something kind of curious. So we need this x to the 4th, we need one more copy of x. Here we need this 1 here. That doesn't have any x's yet. It's a lot to write down, but the idea is sorry, this one also needs an x to the 5th divided by. Did I copy it down wrong? Yeah, this denominator was a 2x. Okay, so sorry, the denominator had an x up to the 1st already, so it needed 4 extra. So there's the x, so I want to factor out this x to the 5th, but then what do I have left over? So I have what I have originally, but then I want to have x to the 5th total. So we've got 5x to the fifth. So finally, if I factor out the thing that already had an x to the fifth I didn't have to multiply and divide by anything. So this one you just get a 3 left over. Basically, the denominator has order of magnitude 5x to the fifth. The x to the fifth factors out. You've got a 5 plus the very small stuff. And this one, I copied that one down wrong. So this 2x, it needed an x to the fourth divided by x to the fourth. So there's a, and I'm missing a 2. The x to the fifths cancel out. This constant divided by x squared, this constant divided by x to the fifth, those are all very small. And the main idea is you have basically 3. You have something that's very close to 3 divided by something that's very close to 5, and then times x to the fifth over x to the fifth. It's basically 3/5. So that's some food for thought, something to think about. But what I'm going to do is I'm going to erase this and the standard fact that this exact same process works no matter, as long as the 2 degrees are the same. You factor out the highest power, and then what's left over is the leading coefficients plus very, very tiny insignificant stuff. And that tells you what happens for x, a large positive or a large negative number. So that's what I wrote on the other side. I think I called it A divided by B. Okay, so that one, that's sort of the main idea there. I want to sketch the idea for when the denominator has larger degree. Let's use a simpler example maybe. So let's, so same idea. F of x is equal to x plus 1 over x cubed minus 1. Well, now x cubed is the only copy of the biggest thing at the party. So the numerator I want to factor out an x cubed. I want everything to have x cubed, so I can factor out an x cubed divided by x cubed. So what do I have? I have in the denominator, I have 1 minus 1 over x cubed copies of x cubed. In the numerator, I factor out those 2 copies of x cubed. Here, maybe I'll write down an extra step here to make it clearer. Okay, the denominator I factor out an x cubed. The numerator I factor out an x cubed. Yeah, so the numerator doesn't have enough. So when I try to factor out an x squared from the numerator, the numerator, what's left of it is also very, very tiny. So when x is a small positive or negative number, the denominator is x cubed times basically 1. The numerator is x cubed times something very tiny. You factor out the order of magnitude from the denominator, and then you factor out that same thing, x cubed, from the numerator. The numerator is so much smaller than the denominator that, like the original, it's like 1,000 divided by 1,000,000,000. It's just the denominator is so much bigger, and one way of seeing that is sort of this sort of logic here. So I'm sort of explaining why once and for all, but the standard factor you can use is that's always what happens. If the denominator wins, then the denominator is just way bigger than the numerator when x is a large number. So plug in large x's. And that's what you get. So, yeah, so we'll save that case for last. I want to look at just these 2 cases here. So no, we don't necessarily have to factor this because with horizontal asymptotes, it's kind of, we can get right to it. So what happens? The denominator is winning. The denominator is a whole order of magnitude bigger. So here's the x-axis, here's the y-axis. And it's something like this, and then it's something like this, and then what happens in the middle is, well, maybe we investigate, are there holes, are there vertical asymptotes, let's look at the x-intercept, the y-intercept, all of that. What I really want to emphasize is that there's this, we know for sure that there's a horizontal asymptote, y = 0. middle, well, we can get a little bit of help. If we work harder, we can find sample points, we can find vertical we can find, the x-intercept and the y-intercept, if there are any such things. We can do all that. Anyway, let's kind of how that goes. Okay, so it's fairly straightforward, so maybe let's just do a few of these kind of quickly. It's going to be a real pain to put everything together to do graphs, so we'll do a couple of those. That'll probably be a long video. So let's try to keep these going kind of fast here. So we'll just double check real quick. This one, it's in reverse order. The highest order term is at the very end. So -4 is that coefficient. The coefficient in the numerator is +3, and that's it. So what happens in the middle, I don't know, but here's y is equal to -3/4, and then yeah, so what happens, it looks like it'll either be like this, or it'll be slightly above or slightly below, or maybe it's allowed to cross even. It could, but it's in behavior is that it's going to be approaching that horizontal line. So if I only want the horizontal asymptote, then I'm already done here. Denominator. So that's really all there is to it. The denominator has higher degree. The horizontal asymptote is y is equal to 0. And maybe let's do one that's slightly critical thinking. H of x equals x plus 1 times x plus 2 all over 2x squared minus 4. So actually, let's make this a little bit more interesting. Let's do that. Maybe let's make that a 5. Okay, so if it's 2x plus 1 times 3x plus 2 all divided by 5x squared minus 4, that is not in standard form, but if we multiply it out, the two middle terms add up to 5x. The constant term is 4. Well, here are the highest order terms, and they're the same degree. So the function may or may not actually be equal to 6/5 at some point in time for some x value, but for very large positive x or very large negative x, y is going to be very close to 6/5. So it's basically 6/5 plus or minus a tiny bit when x is large. And that's it for the horizontal asymptotes. I think I want to take a short break here. I want to do, because long division is kind of a pain, I want to double check my arithmetic to make sure I don't make any mistakes. So I think I'll cut the video here, and we'll handle slant asymptotes as like as yet another video. So let's do that.